Okay, we ready?
Yeah, we're going.
Oh, was all that on? Anyway. No, that's all right. I don't care. Fracture mechanics permits the prediction of fatigue life we went through last time. And prediction of fatigue life and all these other types of below yield fracture is very important because you've got to figure out on what basis you're going to retire a structure from service. And I'll talk about that in a little bit. But also I gave you the example of the hydraulic cylinder from the America's Cup yacht, where relatively small changes in the material's property, changing the heat treatment so that the yield strength went from 73 KSI to 63, and the fracture toughness went from 26 to 30 KSI square root of inch, and the wall thickness went from 3 to 4 millimeters. Those three changes changed the component from something that was hazardous that could just blast and blow apart in a catastrophic manner and spray high pressure oil all over everything and destroy the cylinder so it couldn't operate at all, to one that would leak before break. And the leak might be a small enough leak that you could still get your sail up and still win the race maybe. Maybe you wouldn't get it up quite as fast, but at least you could get it up. So you'd like things that fail in a safe way. Now, there's actually a number of different types of design criteria. One is fail safe, and the other is common one is safe life design. Anybody know the difference between the two? Something that fails safe is something that if it fails, the consequences are not catastrophic. For example, if I've got a building that has redundant structures, redundant beams, I could lose one of the beams. In fact, the World Trade Center is not a bad example. They lost some of the perimeter beams when the aircraft went through the wall, the outer shell, but the building didn't collapse at that point. The rest of the beams held it up because it's a redundant structure. There were 262 or 264 beams holding up the building, so if you lost 10 at one side, the building still held up. And that was a fail-safe design for the structures. You have a lot of redundant columns, not beams, I call them beams, but redundant columns, and you could lose a few of them. One time I had to look at a crack in a 9-foot beam in a, did I ever tell this story, in the approach to the George Washington Bridge in New York City? If anyone's from New York City, there's some like 20-some story apartment buildings that are built right over the roadway. And if you're driving to the George Washington Bridge, you go underneath these buildings. And one time, I was asked to come to New York City and look at this 9-foot crack. It was a 9-foot crack in a 9-foot high beam. This was one of the beams that was holding up this building over the roadway. And it was sort of exciting. That particular section of town, I didn't know anything about it. I just flew into LaGuardia and took a cab out to the address they gave me. And the cab driver dropped me off. I gave him the money, and he sped away. And I looked around, and there was all these little plastic capsules all over the sidewalk that had drugs in them, right? And I'm there with my $3,000 worth of camera equipment, showing over my shoulder and looking around the neighborhood and wondering, why the cab driver, kind of, why did he speed away so quickly? And I started looking at all the graffiti on the walls and realized this was not the nicest area of New York City. And I go up to the apartment building door, and there's this big kind of a steel blast door with about 15 locks on it and bolts and dead bolts and stuff. No one else around, so I knock on the door. Takes a little while the person unbolts everything, and this guy, Hasidic Jewish person, opens up, with his black hat and his long forelocks and everything, and he was the manager of the building. Okay, it turns out that this Jewish group had purchased this building as an investment, and it was great. He also had lots of fun. He also had 7 children, and I have 7 children. We got along great. We went down to see this crack, and they were banging on the beams, on the pipes. The guy was leading us down there through the basement to get out to see this crack in this beam. And I said, "What's he banging on the pipes?" He says, "Oh, you get rid of the rats." Okay, scare the rats away before we cornered one of them or something. Anyway, I went down in one of the basic beams, 9-foot high steel beam. had cracked all the way through, due to stress concentration, by the way, and a poor weld detail, so it created a notch in the brittle material. So that was why the beam had, oh, well, there's also another reason. It took an impact load to do this. Just like in the Northridge earthquake, you can put up brittle steel, and if it never gets an impact, there's no problem. But what had happened was the Port Authority was knocking some concrete off these beams in order to relay the concrete. The building was 25 years old, and the concrete was deteriorating. And so they had this big 2,000 foot-pound ram that would knock the concrete off. Well, they missed the concrete one time and hit the steel beam. And it turns out, you know, that impact in the brittle steel with the little notch detail caused caused a brittle crack to run through the beam, and they lost the beam. But fortunately, it was a redundant structure and a fail-safe design. You could lose one of the beams because there are like 40 of them underneath the building, holding the whole building up. Losing one is not going to bring the whole structure down. Now, the other thing that's interesting about that story, when they went to tell the tenants about the crack, they had a crack in the beam in the basement. After the meeting, all the tenants wanted to go to the basement and get some of the crack. So, just tells you a little bit more about the neighborhood. Anyway, safe life, on the other hand, is when you know that the building or aircraft or car or whatever you're talking about has a component that is going to fatigue, you can't really design around it. Let's take a helicopter, for example, or any aircraft. But helicopters, sometimes they say, are flying fatigue machines. They vibrate a lot. And so you get cyclical stresses. And you know that it's the potential for fatigue and a crack growing is there. And if the crack gets to a big enough size, you want to know something about it. You want to know about it, and you want to remove it from service before the crack gets too big. Well, that's exactly why these types of plots that I gave you before of crack growth rate are so important. Okay, this is crack growth rate curve, and this goes back to the first one on fatigue there. This is the crack growth rate. If I know the stresses in the structure, I can predict how many cycles it will take. I just have to integrate this curve, and it turns out you can integrate this curve, and people do it. I've done it. And you'll find how many cycles it will take, DADN, okay, at a given stress level, for the crack to start from, let's say, 1/8 of an inch in size. Why 1/8 of an inch? Because 1/8 of an inch is a typical flaw size that can be readily detected by most non-destructive testing techniques. So you take a brand new part of whatever the thing is. What do I have as a part? I guess I'll take a MIT ring, a big MIT ring. So if you have a part, you can inspect it and you can make sure there's no flaws in it larger than 1/8 of an inch. You then, if you know what the stress is on the thing in service, and you can figure out how many cycles it's going to take. You can count the number, estimate the number of cycles over a given lifetime, and you can say, okay, I'm going to retire that ring after 40 years. Actually, hopefully it'll be a 40-year, 50-year life, so the person can make it to old age before the ring fails. But if it's an aircraft component, you may say, you know, this part has to be changed every 2,000 hours of operation. That's a safe life type of design. You know that if you run it forever, it will fail. So you basically put a time limit on it. That's safe life. Fail safe is, if it fails, there are not catastrophic consequences. And it just depends on the design. Certain things you can design that way or not, and some things not. For example, medical prostheses, people do spinal fusion. Okay, if people have bad backs and they get the cartilage between the bones gets soft and deteriorates with age, and they start having back problems. Well, one of the things surgeons can do is they go in and they try to do a spinal fusion. It means they go in, they do an operation, they roughen up the bone, they take out the bad cartilage, and the reason they have to roughen up the bone is because bone's a composite material, and the outer surface of bone will not fuse, will not weld to the other bone, as it won't grow together unless you get rid of the top surface layer. If you're taking the other part of the course and you've gotten to the point about surface contamination, well, this you could kind of consider the surface contamination, but you got to get to the soft, spongy inner bone before the cells want to grow back together. Just like your teeth have an outer hard covering, but the living part of the tooth is underneath. Well, bone's similar. So they roughen up the bone, and they want to clamp the bone together so that it'll grow back together. Well, in order to clamp it together, they have some things called pedicle screws. It's just, you call it a wood screw, but they call it pedicle screws because it goes into the pedices, which are these flare bone fittings on the spine, and they go in there with their drill. You know, it's not exactly a Black & Decker or a Craftsman drill, but it's a medical drill that probably costs you $5,000 rather than $50. And they go in there, drill the hole, and they take a screwdriver made out of all surgical stainless steel, puts it in an operating room, and you got to sterilize it, and they screw the bones together. Well, the problem is, nature did a pretty good design in designing the human body to be able to absorb stresses, and putting a high stiffness steel screw, or titanium screw more typically, but could be stainless steel or titanium, putting a high modulus screw in a low modulus material like bone. The titanium or stainless have like 15 to 30 million elastic modulus, and the bone may be a couple million to 5 million. Okay, much different stiffness. We'll put stresses on that screw, and you know that within 6 months that screw is going to fail. It's just, there's no, you know, under the stresses and everything else. You can't put in a bigger screw because nature only made the pedicles big enough to take a certain size screw. So you can't lower the stress. You put it in, but you expect that if all the healing goes properly, the bones will fuse within 6 weeks, not 6 months, and the stress will be taken off the screw, and the screw is not bearing any load once the bone grows back together. They call this the implant race. Whether you heal, you know, and the bones grow together faster than the screw fatigues. Okay? In the medical literature, it's called the implant race. If you're a smoker, your bones won't heal as quick. Anybody know why? It takes oxygen in the blood to heal bones. And smokers have less oxygen in the blood. Okay, so they tell you don't smoke. Anyway, it turns out 1 out of 6 spinal fusions does not take. Okay, it's just the way medicine is. Okay, it's not easy to do. And so they have these screws fail. There was a huge number of lawsuits because 60 Minutes or one of those, you know, documentary programs said, you know, this is, you know, they did a documentary on it, and just all of a sudden billions of dollars worth of lawsuits on this whole thing. Where, hey, if they could have designed a fail-safe screw, they would have. But nature didn't make the human body that way, or the properties of the materials we have to be such. And so it's basically a safe life design. So safe life versus fail-safe are two different philosophies in design. One of them they call retirement for cause in the aircraft industry. You retire a part only if it's got a flaw or a defect in it. So you do inspections periodically. Every 2,000 hours you're supposed to take the engine apart, or every 30,000 hours or whatever it is, you're supposed to go in and do a detailed inspection of the airframe and look for cracks. And you only retire the part if you actually find a defect in it. That's retirement for cause. There's also retirement for time. If the part got to be a certain age, you get at the end of the safe life, and you want to take it out of service and replace it. Yep.
Is there a point where it's cheaper to buy a new plane rather than replace all the parts that are getting old?
Yeah. Yeah, well, and that's not just an airplane, that's a nuclear reactor, okay? It's a car, okay? And obviously it's the same type of philosophy. However, the price of, or the ability to build new nuclear reactors is such that, and the cost of decommissioning is such that that time frame is getting stretched out further and further. So they do more and more inspection. And obviously for an airplane, typically a commercial jet, it's 100,000 hours of operating life. It's kind of just like it used to be for a car. 100,000 miles was kind of the limit. But there are cars, you know, they use Mercedes as taxi cabs in Belgium because they typically drive them 500,000 to 1,000,000 miles. because they like to, they can keep them up. They may replace the engines a couple of times in some of these cases, but it's just a question of overall economics of the whole thing. And those economics change for all kinds of reasons. Okay? Did that answer your question?
Where do those old planes go?
Arizona. They stick them in this old, I don't know if it's a military, old unused military air base, but if you've ever seen pictures during the, after the SALT talks and stuff, we agreed we'd get rid of a certain number of our B-52s, and there's a graveyard out in the desert of Arizona where the humidity is very low, and they would, in order to let the Soviets, this was 10 or 15 years ago, so maybe you didn't see these pictures, but they used to have these pictures in the paper or news magazines every now and then, and basically so the Soviet spy satellites could take pictures and see that we were dismantling our B-52s. They basically would have them in this location, and they would just take the wings off, okay? And so you could see from space that they had dismantled and the plane was no longer functional. However, they leave the parts there for commercial jets because if you really need a spare part on some of these things, you leave it out in the desert in Arizona where there's no humidity and things don't corrode. The corrosion rate is much, much less in a desert than in a moist environment. So they go and park them there. Now, what do you do with other things? What do you do with the ship when it gets too old? And typically the life of a steel ship, an old cargo tanker and stuff, is 30 or 40 years. Well, there's too much, you can't just park them. There's not a graveyard for ships like there is for aircraft. And there's a certain value to all that steel. It weighs enough that there's scrap value. In aircraft, you have the scrap value to the aluminum, and they will get that out eventually, but that's relatively small. They ship them to Bangladesh. And in Bangladesh, they have a lot of low-paid workers who don't know about environmental controls and health hazards go in there with cutting torches, and they just slice the thing up. And that's because nobody else in the world wants to do it because of the environmental hazard of what was the cargo, how many people you're going to blow up, okay, because you don't know all the details of what was held in there, or they're slicing through a pipe that may have something that's explosive in it. So, I mean, it's a very hazardous operation. A lot of the ships that have been coming in are 30 or 40 years old, full of asbestos. You could never dismantle a ship in any country that cares about the health of their workforce. So you ship it to Bangladesh, and you literally ship it to Bangladesh. And actually, the shipping companies basically have some crew, and they just run it aground on this beach in Bangladesh. And then when the tide goes out, these guys go in there with their cutting torches and truck it off, and But you got to remember, it's a country where the life expectancy is probably only 35 or something like that, and people will work for very low wages because you can starve if you have even lower wages, you starve. So it's kind of you don't have much choice. Just another example of exporting our environmental problems. If you have an environmental problem, just export it. Let someone else take care of it. Actually, it reminds me, this kind of hit home to me back in, I think it was 1992, MIT held the World Economic Forum here, which is usually held in Switzerland, and they did this experiment, and I was chair of a session that had the Minister for the Environment of Russia. The Soviet Union had broken up, but he was the Minister of the Environment for Russia, and this was 1992, Detente and Perestroika was in 1985, and things were opening up and things. And someone was asking him about the tremendous oil pipeline problems in Siberia. Anybody know about the oil pipeline problems in Siberia? Apparently only about half the oil gets through the pipeline because the rest of it just leaks out into the environment. Okay, they didn't have enough money to repair the pipeline, but they needed the revenue from the oil, so they just didn't repair the pipeline, and they're just continuously leaking crude oil into the Siberian environment because they need the stuff. And so someone asked him about why they didn't do something about this. He says, you have to understand that in 1985, when Perestroika and Detente was all the Perestroika and Glasnost, Detente was earlier, was all the rage, the Soviet people, or the Russian people, were very interested in the environment. But today, they're only interested in eating. Okay? So if you go back to, anybody know Maslow's hierarchy of needs, right? You have certain basic needs like food, shelter, and clothing. And if you don't have those met, you can't worry about those things higher in the hierarchy. Well, it's just a better example of that. We also had the chairman of Tata Steel. The Tata Group is by far the richest industrial group in India, run by the Tata family. They're worth billions of dollars. And in India, billions of dollars is lots of money. Okay? Someone asked the chairman of Tata Steel why they were so environmentally unsound in producing steel in India. And his comment was, look, I'm sitting on $5 a ton iron ore, which is very, very cheap, very high quality iron ore. And India needs foreign exchange, needs to get foreign money so that we can improve our country. I am going to sell steel on the international market, no matter what it takes. It's sort of like, they like to eat in the Soviet Union or the former Soviet Union. Well, India needs foreign capital, and he was going to sell steel. He didn't want to make it in an environmentally unsound manner. And if other companies in the West or countries in the West would give him the technology to make it in an environmentally sound manner, he would, he said. But he doesn't have the capital to be able to pay the prices that the people in the West want for the technology. So if you give it to him, he'll use it. But if you don't give it to him, he's still going to sell steel. Okay? So it's basically Maslow's hierarchy of needs. So you have to understand that there are different motivations for different people. And a lot of the debates that occur in the world are because people are coming from two different levels on the hierarchy of needs. I mean, just look at what's the World Trade Congress that just, what was it? What's the thing they just, last week they had the big problem, what do they call it? World Trade, World Trade, yeah, WTO. The talks broke down, and the poor world countries said they weren't going to be dictated to by the wealthy countries, specifically the United States and stuff, and they thought this is great. There's a lot of ego there, but it's also because their needs are fundamentally different than what our needs are, because we're at a different level on Maslow's hierarchy. Okay, so there's safe life and fail safe, two different design philosophies, both of them work. This is great for the companies like to sell spare parts. This is not so great. I mean, you build it once and you just have to go and inspect it. In both of them, well, more and more people are trying to extend the time. We're going to talk about non-destructive testing. The reason non-destructive testing is important is because you've got to go in and find the flaws. Either when you first manufacture it, you've got to make sure you don't have big flaws that are going to lead to early failure, or you've got to go in there periodically and do the inspection. And they do it both ways. And so you can say there's, they go in there and do that inspection on these types of things. The Sioux City, Iowa crash was a big flaw that wasn't caught in the initial manufacturing inspection and led to a failure before the safe life time limit. They probably would have taken it out of service. I don't know specifically on that one. I didn't work on it. But to show you the difference between brittle and ductile fracture, this is a tensile specimen from a piece of steel, and this shows ductile fracture. I don't have a brittle specimen because well, there is such a thing as brittle steel. Actually, I may be able to find one, but this one has stretched down, we call neck down, and pulled apart, and when it pulls apart, it ends up with a characteristic what we call cup and cone fracture, and I don't think we need to go through the details of why you get cup and cone. So this is a strength test for the force of fracture. They've been doing that for over 100 years. This is a Sharpie specimen, C-H-A-R-P-Y, named after a French metallurgist of 1900 who invented it. And basically you take a 1 centimeter square by, I think it's 10 centimeter long bar of steel, and you put a little 2 millimeter notch in it, and you whack it with a hammer. But it's a controlled hammer. It's on a pendulum. And you know the weight of the pendulum, and you hit it, and you can see where this one got whacked from the back side. They call it the tup, or the end of the hammer, T-U-P, hit and embedded itself in here. And this steel was nice and tough, a lot of energy absorption. And you basically, all you do is measure the pendulum and find out how far it swings back up. I mean, if there's no specimen there and you take a 264 foot-pound energy pendulum, it swings all the way up to, except for the friction in the thing, which is near zero, it swings all the way up to the same height that as it started from, right? Well, if it hits something along the way, it doesn't swing up quite as far. So you measure the foot-pounds of energy absorption in the steel. This energy absorption, this is impact, because this thing's just falling, a falling weight. This is 1/2 of a brittle specimen. You can see the stretching and the distortion on the ductile one, or the tough one. This one would be called tough. This one would be called brittle. Okay, so that's the difference. Now, one of the insidious things about steel is changes in temperature can change something from being tough to being brittle. Just dropping the temperature by 50 degrees Fahrenheit can have tremendous changes. So I brought you this. Actually, MIT Libraries gets rid of their old books. This is the 1946 book, which was the investigation on the design and methods of construction of welded steel merchant vessels. Report of an investigation. I told you right after World War II, people were interested in fracture toughness of steels because ships were splitting in two. And this is the famous picture of the Schenectady at dry dock. If you look on the page before, here's a ship that split completely in two. Now, some of these did it in the North Atlantic, and they're sitting at the bottom of the ocean with some of the people. And here's the big brittle fractures. Lest you think that this no longer happens, I could have brought another book on fracture mechanics that shows the exact same thing happened in the North Atlantic in 1979. There's a Kuwaiti, I think it's a Kuwaiti tanker, or maybe it's Brunei, or anyway. It was an oil, I believe an oil tanker, just split completely in two. And they actually recovered it because when these things split in two, if the seas aren't too rough, they just kind of split like this, and so the fractured open end is facing the, going up to the sky, and the other end is kind of sitting down low in the water. But in any case, brittle fractures still occur. The Northridge earthquake I mentioned. So it's not as if we've gotten around it. We've done a lot, and we don't have as many failures, but we still have failures. And one of the problems, one of the reasons they hadn't had ships fall apart like that before was because, or does anybody know the reason? It's because they weren't welded before World War II. They weren't all welded construction. They did actually have a very famous ship failure in the first part of the 20th century that was due to brittle fracture, they now know. Anybody know which one I'm talking about? The Titanic. But those were riveted plates. What would happen is typically in a riveted structure, if you got a brittle fracture, and they did get brittle fractures because the steel was lousy quality back then too, before World War II, they would get the crack, it would run through the plate, and it would stop before it got to the, or it'd stop at the end of the plate, and it wouldn't keep running because it wasn't a continuous plate. So when you had riveted structures, it would just crack through one plate. And then you have essentially a fail-safe type of design. You'd only have a small hole in the hull of your ship. Okay, the whole thing wouldn't split in two. If you weld the whole thing together, though, now the crack can run between plates, and it runs all the way around. So it was when they started to completely weld the ships that you could get long cracks. And some of these cracks can get to be very long. There have been brittle fractures in oil pipelines, or gas pipe, I don't know if a gas pipeline, listen. It would occur in a gas pipeline. There have been brittle fractures in gas pipelines that have run for 30 miles. Okay, that's a very expensive break, because once it starts running. And the reason it occurs, it's more insidious in a gas pipeline than an oil pipeline, is because of the speed of sound. A brittle fracture runs at something close to the speed of sound, about half to 2/3 of the speed of sound. Well, what's the speed of sound in a solid? It's around 3,000 to 5,000 meters per second. That means this crack is running, at about a mile per second. Okay, that's fast. Okay. And it turns out the decompression velocity, if I have a rupture, the decompression velocity of a liquid is a similar order of magnitude in speed. And so basically, if the crack slows down for any reason, the stress of the pressurized liquid will dissipate itself because it decompresses at about the same rate the crack is growing. So typically, you get a rupture of a liquid pipeline, whether it's oil or gasoline or water or whatever. Basically, the crack just runs for a few pipe diameters in each direction, and it stops because basically the pressure, the stress is relieved that's driving the crack by the decompressing liquid. The problem is the speed of sound in a gas is about an order of magnitude less than in a condensed phase like a solid or a liquid. Why is that? Because the atoms are further apart, right, in a gas. If the atoms are close together, they interact, and the speed of sound is basically limited by how fast the atoms can reach each other. The typical type of vibrational frequency for a solid material is something on the order of 10 to the 13th hertz. Okay, if I do this properly here. So if I got 10 to the 13th hertz as the speed of vibration of two atoms, and they're separated by one atomic distance, which is something on the order of 2 times 10 to the minus, let's say angstroms are minus 10 meters, right? And I divide all this, okay, or I multiply these two together, so I've got frequency times wavelength equals velocity, right? Is that right? So I should multiply these together, and I get, lo and behold, 5,000 meters per second. Did I do that right? Or 2,000 meters per second. Right, 2,000, if I'm multiplying. 2,000 meters per second. So the distance of separation of the atoms is really 3 angstroms. I get 3,000 meters per second. The speed of velocity in a condensed phase, right? Okay. Oh, just order of magnitude analysis. In a gas, it turns out the atoms aren't vibrating or moving any faster, but they actually are moving at the same speed if you go through the kinetic theory. But the problem is they have to go about 8 to 10 times as far at room temperature. Why do I know it's 8 to 10 times as far? Because the density of a gas, if you take a liquid, take water, and vaporize it, and you could vaporize it at room temperature just by, by lowering the pressure or just by vaporization. If you put it in a vacuum, it would vaporize. But in any case, at typical pressures, the density of the gas is about 1/500th the density of the condensed phase, of the condensed phase. The volume is 500 times greater at room temperature. Okay? So what's the cube root of 500? It's about 8. So the distance of separation in a gas is about 8 times. The molecules are 8 times as far apart in the gas phase as they are in the condensed phase. And therefore, the speed of sound in a gas phase is this number divided by about 8, which is about, well, in air at room temperature, it's 343 meters per second, okay? That's not exact, I mean, that's approximate, right? But we're coming up with similar types of numbers, right? So, in any case, what happens in a gas pipeline is because the gas doesn't decompress as fast as the crack is growing. If the crack is growing at 1,000 meters a second, but the gas is only decompressing at 300 meters per second, that crack sees full gas pressure all the way along. So the brittle crack runs for 30 miles in a gas pipeline, whereas in a liquid pipeline, it only runs for a few feet. So just differences in dynamics. The point of all of this is you actually should know a lot of the types of numbers or be able to calculate the types of numbers to do these types of estimations. I don't, you can tell, I don't remember all the numbers, but I know where they come from. And so when I have to, I can go back and do the order of magnitude analysis. So an important part of engineering is learning to do estimations of things. Questions on any of that? Let's talk a little bit about residual stresses, which is where I was at about this time yesterday. Residual stresses create problems because it was the residual stresses in the Liberty ships that caused these ships to fall apart. Doug, if you want to put that picture, put the picture at some point on the video. I don't know if you got it when I was showing it before, but okay. So other people can see the book, okay. In any case, if I have a thick shaft or plate and I heat it rapidly, there's going to be a temperature gradient. So if this is room temperature and the heat starts to diffuse in from the two surfaces, it's going to be hot on the surfaces and the heat's going to diffuse in. The center will remain cold and this top is hot. The stress, because the material wants to expand when it's heated, the stress is going to be compressive on the outside surface because the material is all stuck together, right? So I get compressive residual stresses, or I get compressive stresses on this surface, on the outside surfaces, and I get tension on the inside. And later I'll actually show you a failure of a ship component that was caused by that. Turns out this tensile area here, underneath this part of the parabola, this is zero stress, on the positive stress, must be equal to those two areas in order to balance the forces. So you can calculate all these things as far as that goes. And oops, going back. So now, understanding that part, you can go and say, well, what happens to create thermally induced residual stresses? I talked yesterday about mechanically induced residual stresses, where you actually deform the surface, and the compressive forces are going to lead to a compressive force on the surface, which is an advantage. It'll reduce the fatigue strength and other things because fatigue cracks start on the surface. But thermally induced residual stresses put things the other way. And it's always very confusing to me and to students to try to say, well, which way the stress is going? Because if you start thinking about what happens at high temperature, well, at high temperature you have this stress state, which is the same stress state I drew before, where you have compressive stresses on the surface because the top surface material, remember I got a temperature gradient going through here. It's hot on the surface and cool in the center. So I get tensile stresses in the center, I get compressive stresses up here. If I magically were to say, well, I'm going to cut the material from the surface where it's tensile, and I recognize that I can induce yield level stresses in the material with relatively little temperature difference. How much temperature difference? Well, we can calculate that. A typical thermal expansion for a metal is 10 to the minus 5 per degree centigrade for most metals. Not for every metal, but you know, steel, copper, aluminum type of structural material. So 10 to the minus 5 per degree centigrade. What is the typical value of strain for yielding of a material, all you mechanical engineers? When we do a stress strain curve, and you go up here and you say, what's the offset to define yield? What offset of strain do we use? 0.2%, 0.002 as a fraction, 2 parts per thousand of strain. It actually may be 4 parts per thousand when you actually take the modulus in here, but you would basically draw a tangent, or not a tangent line, but a parallel line, and come back here and say when the material has stretched beyond its elastic limit by 0.2%. Some people use 0.5%, but in any case, so I multiply that by 0.02 and I get, oops, I don't multiply, I divide here. 0.002 times 10 to the minus 5 per degree C, and I get 200 degrees centigrade temperature change, because I'm just saying the change in length is equal to the change in temperature times the coefficient of expansion of the material, right? So If I want to know delta T, I just take my change in length for yield and divide by the coefficient of expansion. I get 200 degrees centigrade will put me in 2 to 3, usually I just say 2 to 300, will take me to yield level stresses in the material. It does not take a very big temperature differential. It's not 1,000 degrees. Several hundred degrees of temperature will produce yield level residual stresses in most materials, most common materials. Not in quartz glass, which has a 10 to the minus 6 coefficient, okay? That's why quartz, you can take quartz out of the oven and quench it in water. That's why you can take Pyrex, not Pyrex, but you can take Vicor and some other things. Some materials have very low temperature coefficients of resistance, and therefore they can take a lot of thermal shock, okay? In any case, if you take a metal and you heat it up, it will reach its yield stress when the temperature differential is only about 300 degrees. And if I could magically cut the material in two, the material here that yields on the surface would shorten its length because it's yielding in compression. This material is in compression when it's hot, so it shortens its length. So if I just think idealistically, the material in the center wants to elongate, but it's not above its yield stress. But the material on the very edges, which is a higher temperature gradient, will actually compress. It will yield. So this material yields, and it's balanced by the forces of tension in here, but this material in the center doesn't yield. I yield the material on the surface in tension, and yields in tension, which shortens its length. I cool everything down, and now effectively, if these things weren't welded together, the material on the surface is shorter in length than it was originally when I started out. If it's shorter in length, but in fact, it's not idealized with a separation here, but it's still bonded to the internal material, I will end up with tensile residual stresses because in order to bring this shorter surface material back to the original length, because the thing still has not, I didn't really break it like this, this is just to show you conceptually, I end up with tensile residual stresses. The key to all of this, and I've never found it to fail, is whatever stress state exists at high temperature will reverse itself when cooled to low temperature. So all you have to do is figure out for a various complex geometry part which direction it wants to bend at high temperature, and then at room temperature it will have the opposite stress state, okay, because it yields at high temperature, it shortens its length, and that's going to cause it to bend back the other way and end up in tension when it's all said and done. Now, why is that important? Well, anytime you weld, you're thermally inducing residual stresses. What were some of the stresses in the ship plate? Thermal stresses. We talked about the fundamental equation of fracture mechanics that K is equal to sigma square root of pi a. And the problem is, you can calculate what the surface stresses are by finite element analysis. You can't calculate what the residual stresses are very easily. It turns out the world's biggest computers still cannot solve the thermoelastic plastic mechanical problem with the type of accuracy that we need to calculate residual stresses. You can do it in very simplified geometry with lots of symmetry and things like that, but you go to a real part of complex geometry, you cannot calculate residual stresses. You still have to measure them or just experience them. And it's not that easy to measure them. Well, it's easy to measure them if you want to destroy the part, but it's not easy to measure them in a non-destructive way. So residual stresses lead to lots of brittle fractures, like the Liberty ships, like the Northridge earthquake buildings. Residual stresses can be, or not can be, but they would potentially be additive in terms of fatigue life. If I can set up compressive residual stresses on the surface by shot peening the surface of something, that's going to improve the fatigue life of the part. So if I go and shot peen the surface and I compress the surface, I deform the surface locally, that sets up compressive stresses on the surface mechanically. I can double and triple my fatigue life for that component. My only problem is if someone comes along and breaks through that layer, I'm down into a region of tensile residual stresses. There are some heat treatment processes that I might do. For example, the crankshaft of a high quality engine, such as might go in an aircraft for a private plane, they basically, you know, the crankshaft looks a very complex shaped thing that, well, I probably shouldn't even try to draw it. You got, forget it. I'm not even going to try to draw crankshaft. Let's see. Let me draw the mains. So here's the main bearings, and then you're going to have the rod bearings that will be at different levels, and they all got to be connected by different materials in between. So that's a main. So if this is an engine, you'll put a propeller out here, right? And we'll put a gear on the end, okay? So you got some crankshaft. This is a 2-cylinder engine, and these are the main bearings here, and here are the rod bearings for the connecting rods for the piston engine. Well, it's a very complex part, and you want good wear resistance. You also want good fatigue life, particularly if you lose one of these things up in the air. It's not good. Drop like a rock. So they actually, for wear resistance, they nitride the case. So this is a steel part, and they actually take an ammonia atmosphere and they diffuse nitrogen into the surface. Well, as they diffuse the nitrogen, it expands the surface and gives you very favorable compressive stresses. But if I get compressive stresses on the surface, okay, you'll get tensile stress. Well, let's see. Compressive stresses on the surface, you're going to get tensile stresses underneath the surface, because you got to balance the stresses, right? If I've induced tensile stresses, compressive stresses on the surface, which is good for fatigue, I'm going to have just beneath the surface, by a couple of millimeters, tensile stresses. And it turns out both of the big engine manufacturers over the last 5 or 10 years have been having tremendous problems with these tensile stresses and some heat treating defects that occur beneath the surface. And the fatigue cracks start 2 millimeters beneath the surface. They don't start on the surface because you got a good nitrided case. If you didn't have that nitrided case, you would have you'd have a 1/3 less fatigue life on a good crankshaft. But unfortunately, when people forged these crankshafts, they overheated them, and they produced some little flaws that are on the order of only 100 microns in size, but those flaws, if they're right on the surface, are not harmful because they're in a compressive stress state. Okay? But when you add the positive stress state right beneath the surface to the operating stresses, that flaw size gets to be large enough that you get fatigue cracks. And these crankshafts are failing in service. It's a big problem. Don't fly in small planes for a few years. Okay? Well, it's okay to fly on the commercial ones where they have Pratt & Whitney engines, but be careful about Teledyne Lycoming and Teledyne Continental engines and APCO Lycoming engines. Okay, they're the ones who have the problems. And if you have friends that you would like to see again, you might tell them as well. Okay, I guess that's enough for today. I guess I'll see you tomorrow. Thanks.